Okay, everyone. In our class, the Friday's class, we talked about two ways to calculate the rotational effect created by this force F. One way is calculate the torque, the rotational effect, this wiggly using the force and the distance, the axis of rotation right here. From here, how far away the force is. So the cross product between the R cross F is going to give us how big and the direction of this torque, the rotational effect created by this force. So the cross product, the magnitude of the R, magnitude of the applied force, and the sine angle between the two vectors measured from the R to the force F. That's the first way. And the second tool was the Newton's second law way for the Newton's second law for the rotational motion. Net torque is equal to I times alpha, depending on the information of the problem. If you have the moment of inertia I and the angular acceleration alpha, or if you have the R and the F and a way to figure out the theta, you decide what tool to use. Also, in this video, I will show you how to combine these two ways to get to the answer depending on the problem. Okay, so this one is a easy type of calculation, ranking problem based on this guy right here, our first tool. You can see we are trying to rotate around this nut using an applied force from the axis of rotation right here at the center of this nut. How far away is the force? That's what the first thing we try to figure out, the position vector R. And it is nothing wrong extending it a little bit because we need the angle pi. From the R, how much is the force? That is equal to 90 degrees. So right here, how far away, distance R, force is F, sine 90. We are using this formula right here. Second case, from the axis of rotation, how far away this force is. Compared to the shorter distance, this applied force in the case B is too far away. That's why I am using capital R, or the lower case, bigger case R. So I could write the torque in this situation. We are worrying about just the magnitude because we are doing a ranking problem. Distance far away, uppercase R, the force applied is the same F, and the angle from the R vector to the force vector, 90 degrees. The third case, draw the position vector. Always go to the axis of rotation, find how far away the applied force is, and you get R times F times sine 90. It is the same as the case A. A and C are the same. This one right here, this is the angle from the R vector to the applied force F, sine 45. It is the shorter distance again. This situation, this is where some people forget it. Extend this R vector, angle from the R vector to the force vector. That's how it is defined. So it should be this big angle that is equal to sine 120. And again, in the case F, the position vector is really smaller compared to the lowercase r as well. And I am saying R small, force is the applied force F, and the angle is 90, so sine 90. Very simple application here. And when you do that, here we go, R times F, case A, R times F sine 90 is going to be 1. That's what I'm showing you guys here. So A and C are the same. Case B is a little bigger than A and C. Right here, sine 45, 1 over square root 2, sine 120, and again, smaller r. When you do that, just using that formula, R times F times sine angle, you substitute the angle values and you can rank. A and C are the same, and B, far away R, bigger R, has the biggest effect. So This will give you some understanding what we are doing. And also this one we did same exact situation using the same formula as the previous case. We are trying to figure out which direction this guy is going to rotate. If we had the moment of inertia and the angular acceleration, talking about the net torque, okay, go ahead, use that. But we don't have it at this point. This is where we are going to use calculating the net torque, the rotational effect, by this formula. Depending on the information you have the force, you have how far away the force is applied. This is where we are using this formula to calculate the net torque to answer this question. Always from the axis of rotation, draw the position vector. How much is the angle from the position vector to the applied force? Substitute numbers. In this case, we are saying the standard clockwise rotations are negative, counterclockwise direction is positive direction. Same as in physics, in math class, you measure the angles. Distance is 4 centimeters away, 0.4 meters. The applied force up is 30 and the angle is negative 90 degrees. If someone needs, you can take this negative sign out. Totally fine for the sine functions. Even when you put it in the calculator, it will come as a negative sign. This one, from the axis of rotation, draw the position vector, measure the angle. Now it is a positive 90. When you put these numbers in the calculator, this negative value is bigger because it is a 30. This one is just a 20. That's why you have a negative effect. So everyone, I will do one more example in this video. This one is helpful, this formula, whenever you have that position vector, how far away the force is applied, how big is the force, you can figure out the angle, go with that. Okay, so this one right here, unwinding spool kind of a situation. What do we do? I'm going to do this problem and also to show you how we can extend this problem. Definitely must watch, must practice, everyone. It will help you in the homework problems as well. So look forward to the exam. This one right here, very easy, even without doing anything. I will show the math way. Even without doing any math, you can say, if something is freely falling, it should be just falling freely with the gravitational acceleration. It is accelerating downward with the G, gravitational acceleration, nothing attached. Some things, the spool or anything dropped downward. But this tension force, with the gravitational force, it will try to go down, but this string, this thread is trying to hold it. That's why even without doing any math, you can say the spool is going to accelerate downward because of this holding. It is going to slow down. It is accelerating downward at a lower, less than gravitational acceleration rate. Okay, that's the conceptual way. Now let's jump into math. We can start by labeling forces on our object of interest, this spool. There will be a tension force. There we go. It is going to rotate, going down, rotating around this center. That is going to be the axis of rotation for our rotational calculations. Moment of inertia, the torque, everything. Now, it has a radius r, and it is going to accelerate downward. This is where everyone, tangential acceleration equals r times alpha, the angular acceleration, the connection, tangential or the linear acceleration and the angular acceleration connection. I want to show you guys how to apply. So alpha and the A connection. The spool is going to accelerate downward, moving downward. That can have a linear tangential acceleration, AT, if you want to call it. Also, this guy is going to rotate, spin, and going downward, similar to rolling without slipping motion. Rolling motion, roll, going downward. Now, you can consider the motion first the linear motion, you could apply F equals ma, our familiar guy, downward to this spool. It comes, there's a force of gravity mg downward, force of tension upward acting, that's why negative, equals mass times the linear acceleration. We don't know this acceleration A, and again, we don't know the tension. That's one of the things we are trying to find, the acceleration. And in the way, we have to figure out how big is this tension. And to find a substitution for the force of tension, let's consider the torque. The object is going to rotate, even though it is moving downward, it is going to rotate around the axis of rotation, this center. We can apply, there we go, you can see I'm trying to do that position vector, the force, that idea to calculate the torque right here, R times F, the cross product. There we have the distance is R, the applied force is F, the angle is 90 degrees. The next force applied mg is at the axis of rotation. When you do the same thing, distance becomes a 0. That's why it is not doing any effect to the rotation. No, nothing. It is going to be a 0 rotational torque effect by the mg because R is going to be 0 for the mg force. Now, sine 90 equals to 1, R times the force of tension. And this is one way to get there, R cross F. And we had torque equals I times alpha, rotational Newton's second law. We can bring them together. There we go, I times alpha equals R times F we found from this cross product. Here we have more and more things coming in. We are trying to figure out how big is this A, the linear acceleration. That's why I am going to substitute for the alpha in terms of the A. I equals, alpha is equal to A divided by R, do the substitution here, times everything right hand side is remaining. So we have force of tension substitution, I, moment of inertia, A divided by R squared. You can go ahead, substitute here. You can get a term A equals what? To do the comparison. I'm substituting from my previous slide right here for the force of tension in terms of moment of inertia, acceleration A divided by the radius of the spool squared. Now we have, bringing this guy to the right-hand side, everything common comes outside, A, acceleration A equals mass divided by mass plus something. This guy less than 1, mass divided by something bigger. So 0.9 something, 0.8 something times the gravitational acceleration. That's why we can say the spool is going to accelerate downward with a lower rate. A is lower than the gravitational acceleration. Everyone, this is the longer way to argue for that problem. With that, I could, and again, here's the problem, I could extend the problem. I could give you guys information about the moment of inertia. And I can ask you guys, find me numbers for the acceleration, for the tension, for the angular acceleration, alpha. When you have that, you can substitute for the moment of inertia I using this one, mr squared divided by 2. When you do the simplification, mass is going to cancel out. Here you have a final version. Acceleration A, if you want to call it a linear, a tangential acceleration, here we go, that is equal to 2 goes to the top, 2g divided by the 3, mass cancel out, 2 times 9.81 divided by 3, you have a final number. If the longer problem asks you, find the tangential acceleration. Next one, tangential acceleration or the linear acceleration was equal to radius times the alpha. Here we can find alpha is equal to A divided by R. A is this guy 2 times G divided by 3 divided by R. All you have to do, A number divided by the radius of the spool. If it is 0.5 meters, 10 centimeters, done, you have a number. Find how big is the tension. You substitute for the moment of inertia. You already found the A, tangential acceleration. You have a final version, force of tension. I'm just substituting for the moment of inertia, for the acceleration A from here. You will get 1/3 M times G, that is the force of tension. So everyone, please redo these problems to practice. This will help you do the homework problems and confirm what we learned, conclude what we learned from the Friday's class.